Welcome. Our first use for a linear approximation is going to be to estimate value of a function. So we want to use a linear approximation to estimate the number square root of 80. Here we have all of our steps. This is in your notes. Step 1 is to decide on f of x. F of x is just the function that is represented by the value we want to approximate. So of course f of x is the square root of x, right? That's our equation. We need to decide on x naught. It needs to be close to x, but easier to work with than x. All right, so x is 80. I don't know what the square root of 80 is. That's not very easy to work with. But I do know the square root of 81. It's pretty close to 80, and it would be a lot easier to work with. Find the change in x. Right? So the change in x is going to be the difference. Right? We were working with 80. We're going to use 81 to approximate, so that would be -1. All right, so now let's find the derivative. Right? That's going to be part of our linear approximation model. Right? As a reminder, all right, our tangent line or our linear approximation formula is our value plus the derivative times the change in x. Right, so our derivative is so f of x is x to the 1/2. Right, we'll rewrite that. The derivative, just use the power rule, would be 1/2 x to the -1/2. And then let's simplify that. So f prime of x equals 1 over 2 square roots of x. Right, power rule, we just reduce the exponent by 1. Calculate f prime of x naught. Right, so f prime of an x naught is 81 would be 1 over 2 square roots of 81. That's just going to be 1 over 2 times 9, or 1/18. So now we'll just substitute. We have all the values we need. All right, we have the pretty value for our function. We have the derivative for the evaluated at that pretty value, right? And we have a change in x. So the approximate value of 80 is going to be we're going to plug it into so f of a, we're going to plug that back into the function, is going to be the square root of 81 plus 1 over 18 times the change in x is -1. Right, now we'll simplify that. So that would be 9 plus, and actually let's just make that minus because it's going to be negative, minus 1/18. Do get exact values, right? So don't have rounding errors in rounding. Don't make the rounding make it more approximated, right? So instead, get an exact answer. Let's change 9 so it has a denominator of 18, so we can combine the two. So that would be 162 18ths minus 1/18, and our final answer is 161 18ths. Let's see how close that really is to the actual value. Right, so square root of 80 is 8.944, so forth. Let's see what 161 18ths is. $8.94444. Pretty close, right? So this won't be exact, but it'll be pretty close. And the closer we are the closer that x naught is to x, the better approximation we have. We won't test them all out, but I thought we would just see that one. And if you wanted to go, if you were like, how close was it? Right? Because I clicked off the board, you can always rewind me and see how close, what was the square root of 80 compared to 161 18ths. I think it differed on the third decimal. All right, so approximate the cube root of 27.1. All right, so decide on f of x. Of course, f of x is going to be the cube root of x. Decide on x naught. It needs to be close to x and easier to work with than x. Well, I don't know the cube root of 27.1, but I know the cube root of 27. Find the change in x. All right, so we have change in x is 27.1 minus 27, and that is 0.1, 1/10. Now, here's a logical way you can think about it. All right, if we're approximating something smaller, we should be subtracting a little bit off our, square root of 80 obviously is going to be smaller than the square root of 81. We should expect to subtract a little off, right? Otherwise, we're going to be too big. Here, the cube root of 27.1 should be larger than the cube root of 27. So we should be expecting a positive change in x because we're going to add a little bit on. Right? So if you ever get stuck which way it goes, that's how you can remember it. If the value you're approximating is smaller, expect the change in x to be negative. If the value you're approximating is larger, expect the change in x to be positive. Right? All right, so now we want to find the derivative. Right? So f of x equals x to the 1/3. Let's rewrite that. And so the derivative, just use the power rule. The exponent moves in front, reduce the exponent by 1. So that 1/3 minus 1 would be negative 2/3. Let's rewrite that. So f prime of x equals 1 over, and I guess I'll put that into radical form. It'll be easier to evaluate for me anyway. That would be 3 cube roots of x squared. Doesn't matter, by the way, where that square goes. Oops. But it could look a little nicer than that. There you go. All right, so now calculate f prime of x naught. So f prime of 27 would be 1 over 3 times the cube root of 27 squared. All right, so that's going to be, oops, somehow we lost the 7. 1 over, and that would be, so the cube root of 27 is 3, and 3 squared is 9. So that's going to be 1/27. All right, so now we'll substitute into the tangent line approximation form, or the linear approximation form. All right, so we've got so f of 27. Actually, I should have put, and I should have done that in the last one. Let me fix this. Yeah, I did put 80. Okay, I almost thought I put 81. So we're approximating, right, 80. Right? And I really should have, instead of equals, I really should have is about. That's all right. So using our linear approximation, we know it's not going to be exactly the same, but it's going to be close. So f of 27.1 is equal to, or is approximately equal to, the cube root of 27 plus 1/27th, and it would make sense for me to rewrite 0.1 as 1/10, since we're dealing with fractions here. All right, so cube root of 27 is going to be 3, and then we've got plus 1/270th. Let's change the 3, so it's got a denominator of 270, so that's going to be 810. Plus 1 over 270, which is 811/270ths. All right, that is the approximate, very, 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 very close value to the cube root of 27.1. And we're able to find that, right, because we're taking this function, the cube root function, and we're turning it into a line. And we can represent any function with a line so long as we stay really, really close to some point. Soon as we get too far away from that line, our approximation method is not very good anymore. All right, so use linear approximation to approximate natural log of 1.1. I think all of these are in your notes. Could be wrong, but I think so. All right, so first let's identify the function. So it's going to be f of x equals natural log of x, right? That's what our function would be. All right, identify x naught. It's your nice value. All right, I don't know what the natural log of 1.1 is, but I do know what the natural log of 1 is. Right? I put so obviously the order you put your steps in doesn't matter too much, because I have find the change of x all the way down there at 6. Right? We could do that. We could do that right now. All right. So we're expecting something positive, right? Because we're approximating a value that is a little larger. So that's just going to be 0.1 or 1/10. All right. So now let's find the derivative. All right. So f of x is right up there. F of x. Oh, actually, I wrote it over here. I gave myself space. So f of x was natural log of x. The derivative for natural log of x is going to be 1 over x. All right, so now let's find f prime of x naught. Right, so that's going to be f prime of 1, which is 1 over 1, which is 1. This is going to be pretty easy, isn't it? All right, so now let's find, we haven't found, well, we could put it all together, and all the other ones I put it all together, but we could find it up here. Since I wrote it as a separate step, all right, we'll find it up here. All the other ones, right, I put it at the bottom right there, right? We found right here, right, we found what the cube root of 27 was. We'll just find it up here. All right, so that would be natural log of 1, which is 0. All right, so our model here is going to be, so I'm just going to write in 0 as opposed to natural log of 1. All right, so we are approximating natural log of 1.1 there. And that's going to be equal to, I can write it again, natural log of 1, which is 0, plus the value of the derivative, so f prime of x naught, which was 1, times the change in x, which was 1/10. So this is just going to be 0 plus 1/10, and I told you it would be easy to figure out. 1/10 it is. Right, so there wasn't too much to that particular model. So the natural log of 1.1 is just about 1/10. And we can check that out with the calculator, I think. This is not the greatest calculator in the world. It's backwards. Yeah, there it is. So let's see. I think I have to hit the 1.1 first and then hit natural log. All right, so we get 0.095. So notice that is not too much different. I must make that negative. And then add, we got 1/10. So that's how far away our approximation was to the actual answer, 0.004689. And you might think, why didn't people just use a calculator? All right, well, this has more uses than just being able to calculate out values, first of all. And second of all, there was no calculator. Right? So here they could do really complex calculations, and it wasn't very difficult. Right? It's as easy as finding a derivative and finding a nice value, and using the linear approximation method. All right, so we're going to use the linear approximation method to evaluate sine 32, a not so nice number. We better use a nice number to help us out. All right, so decide on f of x. These are obviously pretty easy, right? F of x is sine x. Right? It's just without the value in. Decide on x naught. It needs to be close to x and easier to work with than x. Change degrees to radians for trig functions. All right, so 30 degrees. If you don't remember how to change that you would just, so to change it to radians, you would just multiply times pi over 180, just in case you forgot. And so that's pi 6 radians. All right, this is the 30, so your nice numbers are multiples of 30 are multiples of 45. Those are nice numbers. All right, so 30 degrees is a very nice number. All right, if we think about, so by the way, our x naught is going to be 30 degrees or pi 6 radians. All right, so if this is 30 degrees, opposite the 30 degree or pi 6 angle is 1. The other leg is the square root of 3, and the hypotenuse is 2. So that makes sine pi 6 or sine 30 equal to 1/2. That's pretty easy to work with. All right, so and we're not going to be able to work in radians because, well, I guess we could. Yeah, we'll be able to work in radians. We'll just change 32 to radians. What am I saying? So we can change anything we want to radians. It's just not going to be that pretty. We'll change it to radians. 32 times pi over 180. That's, let's see, they're both divisible by 4. So that's 8 pi over 180 divided by 4 is going to be 45. And that's as simple as it gets. So that's our change that is 32 degrees in radians. The change in x is not that pretty. Pi 6 minus 8 pi 45ths. And I'm thinking, why didn't I keep it in degrees? Because we usually work with radians. We don't usually ever work with degrees. So let's see. That would be, we have to change that to radian, to a common denominator. And I have to go grab a calculator. All right, so I found one that doesn't work. I see one. Let's try this one. This one works. All right, so does it work well? You can't read half the numbers. All right, one more try. A calculator that works. All right. I need to bring some good calculators in. 45 times 6, 270. All right, so we want, oh, and actually we could have something smaller than that, 270, because they're both divisible by 3. Let's see. All right, this is 3 and 3 and 5. This is 3 and 2. So the least common denominator, I didn't need a calculator, is going to be, because I don't want the most common, we want the least common denominator. So we're going to need a 5, a 2, and 2 3s. So that's going to be 90. They're both divisible. 90 is divisible by both these numbers. That's what I'm trying to say. So that's going to be, it's going to go in, so 15 pi 90ths minus 16 pi 90ths. So now this is not looking so bad, is negative pi 90ths. There we go. Whew. All right, so that's what it is in radians, negative pi 90ths. All right, so now let's find the derivative. That'll be easy. All right, so f prime of x is equal to, so actually let me write f of x first so you can see them together. F of x equals sine x. The derivative is cosine x. Let's find f prime of, so we're finding f prime of pi 6. So that would be cosine pi 6. Well, that's just going to be, instead of the 1, it's going to be the square root of 3. So that's going to be equal to square root of 3 over 2. And now we can just use our approximation method. So we have we're approximating 32 here. approximate value of 32 with that particular function, or I guess you could put sine 32, is, all right, so we have sine 30 plus, and we had, excuse me, not sine 30. Eight pi 45ths, let's get that into radians, is equal to sine pi 6 plus when we evaluate the derivative, we get the the square root of 3 over 2. I don't know, my math doesn't want to work today. And then times the change in x, that was negative pi 90th. And we're approximating something larger, so we're going to expect something negative. Now all we got to do is simplify. So sine pi 6, that was just 1/2. And then plus, all right, so let's see, we could really not simplify that very much, could we? That's going to be minus anyhow. Minus pi square roots of 3 over 180. If we want to make that, and I'm fine leaving it like that because that's the exact answer. We could make that one fraction, however. 1/2 is 90, so this, we also could write this as 90 minus pi square roots of 3 over 180. And there we go, and I think that one is good. That took longer than it should have. A, I didn't really need a calculator. And B, which I couldn't find. And B, I kept getting tongue-tied. And we're going to do one more on this video. All right, one more on this video. Estimate the value of a function given x naught. So we want to find the linearization of the function f of x equals the cube root of 1 plus x at a equals 0. And use it to approximate the numbers, the cube root of 0.95 and the cube root of 1.1. And that's all we're going to do for right now. In terms of answering the question, are they overestimates or underestimates, we'll come back to that part. All right, and because we'll have some ways to calculate that part out. All right, let's look at the first one. Oh, and by the way, on that last one, I should have, and I didn't, put that on a coordinate plane. All right, so 30 degrees, pi 6 is in the first quadrant. It is positive, and it's a 30, 60, 90 triangle, with the 30-degree angle being the opposite. All right, so now let's do, well, so we'll do one, then the other. All right, so first of all, let's find the change in x. We've got two changes in x. We've got one for each of the problems there. All right, so we've got, so our x naught, so this is our x, and then our x naught is going to be 1. It's given to us in a very odd way there, but our x naught is 1. All right, so we already have x naught, so we don't have to find x naught. It's given to us. It's also, the function is also given to us as well. So we have change in x is going to be 0.95 minus 1, or negative 0.05. For the second problem, change in x is going to be 1.1 minus 1, or 1/10. All right, so the derivative, however, is going to be the same no matter what. So find the derivative. All right, so our function is the cube root of x, because x, that other part of there is just 0. All right, so f of x is the cube root of x, which could also be written as x to the 1/3. And so the derivative is going to be 1/3 x to the negative 2/3, which we could rewrite as 1/3 times the cube root of x squared. All right, so now calculate x naught, f prime of x naught. All right, so that's x naught is 1. No matter what, x naught is 1 for both of these problems. All right, so we have f prime of 1 equals 1/3 times the cube root of 1 squared. And so, well, that's just going to be 1/3. And then we'll substitute into the tangent line approximation formula to find the equation of the tangent line. This is the same thing in step 4 and step 5. Oh, well, here, we'll do cube root of 0.95 for step 4, and we'll do the cube root of 1.1 for step 5. There we go. All right, so this is going to be equal to, all right, so in both cases, our f of naught is going to be 1, right, because we're using this right here. So it's the cube root of 1. And that's pretty close to 0.95 and to 1.1. Plus, right, so we evaluated the derivative at that same value, and we got 1/3, times the change in x. Right, so this would be times negative, and let's change that to a fraction. 0.05 is 1/20. All right, so this is going to be equal to, oh, and I did forget to put in one little thing. There we go. All right, so L of 0.95 is 1, and then minus 1/60. So that's going to be 60/60 minus 1/60. That is going to be 59/60. Let's do the other one. All right, so 1.1 is approximately the cube root of 1 plus 1/3. And now we have 1/10, and that is positive, right? Because we're approximating to something that's more, so we expect to add a little something to it. All right, so L of 1.1 is approximately 1 plus 1/30. So that's going to be equal to 31/30. Right? And we expect to get something that's a little less than 1 for the cube root of 0.95. And we expect to get something a little more than 1 for the cube root of 1.1, given the cube root of 1 is 1. All right, and that's where I'm going to end it. And so I'll see you in the next video, and we'll do some more with linear approximation. Thanks for watching. Bye for now.